All right, our next speaker here is Dan Uden. Dan is a postdoctoral research associate with the Nebraska Cooperative Fish and Wildlife Research Unit at the University of Nebraska-Lincoln. There is a spatial ecologist whose current project focuses on mapping vegetation transitions in western U.S. landscapes. Help me welcome Dan.
Thanks, Jeremy. I'd like to take a moment to acknowledge my co-author, Dirac, who just gave me a kind of a great intro to this stuff, and as well as a number of essential collaborators, Jeremy Maestas with the NRCS, Craig Allen, University of Nebraska, and then Brady Allred, Matt Jones, Dave Noggle over at Montana. We just started this project back in May, and all along the way they've just provided essential input and creative ideas and just various forms of support. Grateful for that and excited to continue the work on this. So to the work on transitions, or regime shifts as they're also often called. I'll use those terms interchangeably throughout the talk. Regime shifts exhibit cross-scale spatial temporal order and the ability to better understand, to track, and even to forecast regime shifts according to this order could greatly contribute to the management of ecological systems. And in rangeland systems, several iconic transitions you see pictured here involve the conversion of perennial grassland to bare ground. You could also have changes from shrubland to annual grassland. We could also imagine perennial grasslands to trees. When they occur, these all unfold as spatially contagious processes, often and with clear spatial order. And there's an ever-increasing literature on regime shifts filled with theoretical advances, methodological advances, reviews of techniques for grappling with these transitions and regime shifts within and across scale of organizations and ecological systems. Dirac spoke a lot about that. So the theory is alive and it's moving. And we're also, as Brady gave a nice introduction to, we're also seeing advances in data. And what advances in data allow us to do is to actually go out and apply theoretical advances, methodological advances in real-world systems. Previously, there are all these, in the study of regime shifts, these prior data limitations, or we're forced to accept trade-offs in the data. For example, in land cover data, Than was getting at this a lot too, that if you have data over a large geographic area, your resolution tends to be poor. And even if your spatial resolution is good, your temporal resolution is probably poor. So you might even end up with a high quality snapshot, a photo of what's going on. But given the temporal nature of these changes, what you really need is more of a video across time to tell you what's going on. And while now those key data and monitoring limitations are being overcome, and a great example of that is the Rangeland analysis platform, where we have spatial extent subcontinental, spatial grain 30 meters, temporal extent multi-decadal, temporal grain a single year with the potential to perpetually update in the future. And not only that, you have various plant functional group estimates all in the same place at different points in time. We've just never seen anything like this in the study of regime shifts, at least not terrestrial ones. So this is just very exciting. And Brady also got at this quite a bit, but the advances in computational capacity. Traditionally, resilient science and regime shift studies have been small scale, number one, because of the data limitations, but also because of computational limitations. If you had the data, what would you even do with it? So that's all coming together now with these advances in geospatial, cloud computing, supercomputing. We can now design and conduct analyses with number one, that are informed by the theory, and number two, with great data over large geographic areas, long time frames. And so this is all kind of coming together at once. And that really takes us to our mission here, which we're integrating recent advances in theory, data, and computational power to detect and image cross-scale transitions in rangelands of the western U.S. And what that that allows us to do here is that's just, I'll go back. I mentioned, so we've got the theory, we've got the data, and we've got the power, and that's great, but what is our metric? Like, how are we actually deriving this, and how are we doing it? Well, when we think about a metric and what we want out of a metric, we know we want a couple things. Number one, we want something that's objectively derived. We don't want subjective decisions, assumptions, thresholds, all layered throughout our methodology as much as we can help it. And we also want something that's transferable. So in other words, we want something that, even back to Than's example between Arizona and Montana, we want to know something about a transition. We want a metric that tells us what we need to know about a transition in Arizona in the same way that it tells us what we need to know about one in Montana. And what we've really come to is this cross-scale spatial covariance. And Dirac gave a nice kind of introduction to this. But what spatial covariance does is it describes the spatial association between two plant functional groups in a given area. So you could also think of that as just a statistical correlation. Are they positively or negatively correlated with one another in an area? So if they both tend to go up together or tend to go down together in that space, that's positive spatial covariance. But if one goes up and one goes down, or vice versa, that's negative spatial covariance. And a spatial covariance of 0 means there's really a lack of any sort of relationship between them. So to make it a little more tractable, maybe, Dirac talked about blowouts in the Nebraska sandhills. And if you've never been to a blowout, it's like a sand trap in a golf course. It's an area where sand, bare ground, meets vegetation. And they kind of tend to have a hard boundary. So imagine that you walked out to a blowout and you stood right on that boundary and you looked to one side. What do you see? Sand, like barely any grass. So it's like 100% bare ground, not much grass at all. Now you look to the other side, what do you see? You see a whole lot of grass, not much bare ground at all. So that, where you're standing, is an area of strong negative spatial covariance, those red areas on those maps that Dirac was showing, because one's going up and one's going down, one's going up and one's going down. And but then imagine if you walked out into the middle of the blowout and looked right around your feet, what would you see? You'd see all bare ground. That wouldn't have the same signal because you don't have it co-varying with the grass in that space. But then imagine that instead of just looking at the area around your feet, kind of as Brady was saying, you could see for hundreds of thousands of hectares around that blowout with the satellite data. Then what would the spatial covariance between bare ground and perennials be? Or between any other functional group? Well, it's really hard to imagine, but we can reason that the answer would change based on how far you could see, based on how much information you were taking in. So that's what we are doing for every rangeland pixel in the western US. We're answering that question at multiple areas, over multiple neighborhoods or multiple scales. I'll call these scales from now on. And so what we're doing, similar approach to Brady and Matt, is using Google Earth Engine to compute this. And we've currently done it for 18 years, from 2000 to 2017, for 10 different functional group combinations with RAP data, over 5 window sizes. Actually, this slide is out of date. We've moved to a 6th window. And so we now have over 1,000 images. And even as we speak, it's running on computing more. And so it's thousands of hours of computing running around the clock. And then we can begin to get these signals, these transition signals, lack of coexistence. We can look at the national or biome level. We can look at ecoregions. We can look at properties. But there's a whole lot going on here. That's a whole lot of signals and a whole lot of data storage and everything else. So how do we deal with all this complexity? And Dirac got into this pretty well. But one way in which we started to do that is adopt the practice of screening for medicine, where screening is used to identify the presence of a disease before its signs or symptoms are manifested. Whereas that's different from diagnostic testing or diagnosis, where you use those signs and symptoms and other information to confirm the presence or absence of a disease. Well, what we're doing is screening for regime shifts. at multiple scales in rangelands. And we do follow this workflow where we first ask what we're concerned about, and then we look for the signals of what we're concerned about. Is it absent? We don't need to worry. Or is it present? Okay, we're perking our ears up. And then if it's present, is it transient or persistent over time? Again, if it's transient, that's not much concern. But if it's persistent, they're going to look a little closer. And now if it's present and it's persistent over time, is it stationary? Does it not move? Or is it non-stationary? Is it moving and changing through time? And that's what we're really concerned about and what we want to detect early on. And so what this allows us to do is screen for regime shifts of national importance. Here you just have kind of the bookend years of our analysis, 2000, 2017. We have all the years between. But we can look at all these different plant functional group combinations, shrubs versus annuals. You see, again, in these areas, red is areas of strong negative spatial covariance. That's where, in this case, shrubs and annuals are failing to coexist with one another in this space. And what you see between the years is that gray areas or these bluish areas, some of them start to turn yellow, and some of the yellow areas start to turn red. And so, you know, in 2000, mostly the activity seems to be in the Great Basin, maybe northern Nevada, and then over time we're looking up here in Oregon and Washington, and even a bit out here in Wyoming and Montana. So we're seeing those signals. In the same way, we can look at perennials versus trees, and again, you see non-stationarity over time, where we're seeing this signal move up from Texas and southern Oklahoma into Oklahoma, Kansas, and Nebraska. And but you know, to make it maybe a little more applicable on a different level, we can look at the extent of ecoregions. And here is an area that was maybe a little bit yellow in 2000 in its perennial tree covariance, but it's bright red in 2017, but only over a small area. This is the Les Canyons region of Nebraska, an area which we're familiar with. It's range dominated, but there's increasing tree covers via the spread of eastern red cedar, and that threatens rancher livelihoods. So as Drac mentioned, these landowners are banding together. They've begun to do that to start managing at a larger scale, to scale their management up to the extent of ecoregions. And they might be concerned initially about a couple of different transitions in the Les Canyons. They might be concerned about erosion, bare ground versus perennials, or they might be, as we've kind of seen already, concerned about these spreading trees, perennials versus trees. Well, we can calculate these covariance signals at different scales or different window sizes. So this is the broadest area, 113 by 113 pixels. It's pulling in all this information from surrounding landscape. And what you end up with is there doesn't seem to be a whole lot going on with a bare ground perennial, but at these larger scales, the perennial tree, you get these big blobs because it's this kind of broad scale change. But as you move down in these scales, we start to be able to just almost trace individual patches of trees. So to make this a little more tractable to management, maybe you can look at a landowner and say, well, you're not actually experiencing change where you're at, and your neighbors aren't even experiencing it, but their neighbors are experiencing it. So it's a spatially contagious process, and it's not at your door yet, but it's going to be there in 5 years. And so you could do this, and then but other people, they've only ever known for, maybe decades that they've dealt with this issue, and so you can kind of prioritize decisions according to that. But what we'll do is, I haven't shown you kind of the view over time. We can run through some quick videos of these transitions at the different scales. I'll just use these two different scales as an example, but you see the bare ground perennial covariance signals. You saw a big blurb there in 2002. That was actually a wildfire that we picked up, but other than that, you see some kind of speckling in and out, but nothing that really appears to be present, persistent, and non-stationary. There's that wildfire again, but it's gone in the next year. So there doesn't, from a screening perspective, I don't think we really need to worry about that one. Now you can see what's coming with the perennial versus trees. Look at that over time. There's a lot of management going on in this landscape. So there's landowners are working, the trees are spreading, landowners are fighting them back, wildfires are occurring, droughts are occurring. There's the drought in 2012. But you can see the differences between the scales, the information we get. This is, oh, you're in the danger zone no matter what here. But a landowner might say, well, I don't have any trees on my property. It's like, yeah, but look a little farther out. You're in a sea of trees. And so we can use this, again, to kind of prioritize decisions. So just to kind of give an overview of this, the current stage we're at, we are screening, we're able to image and track regime shifts across scales of organization, and this is really emerging from those critical linkages of theory, data, and computational power. And to make it a little more effective, maybe even like just in our brains to be able to grapple with it, we're saying, well, this is really, we're screening for these regime shifts. And we're working on, and we're continuing to work on ways to integrate over time, to integrate over space, and to visualize those changes. So you kind of end up going into, making these two-dimensional images for multi-dimensional data. So yeah, it's very exciting, and I'd be happy to take any questions or bounce you to collaborators in the room who, who are building these tools that we're using. So thank you.